We're going to discuss a very important result in mathematical statistics called the central limit theorem. It is the one result on which probably at least 90% of all inference rests. It's a very, very, very fundamental result. That's why it's called central. Okay, before I present that though, I actually want to show you a more general result. This is a result that is more general than the central limit theorem, and it pertains to maximum likelihood estimators. The reason why is because the maximum likelihood estimator is always the estimator of choice. If we're given our choice among any estimators, we'll almost always choose the MLE. And the reason why is because it's asymptotically unbiased and it asymptotically has the lowest variance, therefore making it the uniformly best estimator in general. Okay, so here's what this statement about the MLE says. It says that if phi hat is the MLE for phi, then the standardized random variable for phi hat. Okay, so what does standardized random variable mean? It means I take the variable and I subtract off the mean. Well, if phi hat is the MLE, what's the expected value of phi hat? Phi. So I'm taking this random variable phi hat, subtracting off the mean, and dividing by the standard deviation of phi hat. This is what it means to standardize a random variable. Then this quantity, as the sample size small n approaches infinity, this quantity approaches a standard normal random variable. Okay? The significance of this is several-fold. First of all, the central limit theorem follows as a direct consequence, which is something that we'll show. It's used in hypothesis testing for the population mean, but it's also used in hypothesis testing for the population proportion. Okay, and it can be used for many more general situations than this, things that the central limit theorem does not directly apply to. Okay, a few comments. First, this quantity is generally called a test statistic. Okay, this standardized version of the estimator. And the second is that the standard deviation of phi hat, this is what the sigma phi hat is. Okay, this is generally called the standard error. Okay, and so we're going to use this term a lot. Okay, notice that what we're saying is we're saying that phi hat has a normal distribution. Okay, so this is like the standard deviation of that sampling distribution. Okay, all right. The central limit theorem. So what does it say? Well, it says the following. It says that if we have a random variable x with a defined mean and a finite variance, then the following quantity, okay, basically this is the standardized version of x bar minus mu divided by its standard error, which is sigma over the square root of n, goes to a standard normal as n goes to infinity. Let's see how we can apply this. There are two cases we have to think about when we're looking at this quantity. What we really want is we want the distribution for this standardized random variable for x bar. When x is normal, this is actually quite simple. When sigma is known, the central limit theorem, and in fact we don't even need the central limit theorem. When x is normal, this is automatically true. This does not involve the central limit theorem. This is a property of normal random variables. Okay? Independent normal random variables. When sigma is not known, again, we don't need the central limit theorem for this. It just says that the standardized version, where now I have to use the sample standard deviation in place of the population standard deviation, it looks like a t-distribution with n-1 degrees of freedom. Okay, so we're not using the central limit theorem here. This is a property of normal random variables. But when x is not normal, we do need the central limit theorem. And when n is greater than 30, we say that the standardized version, and we also know the standard deviation, we say that the standardized random variable approaches the normal. If sigma was not known and we had to use s, we would say it approximately approaches a t-distribution. Okay, when n is greater than 30. When n is less than 30, we can't say anything about the distribution of the standardized test statistic. Okay, so here is where we're using the central limit theorem. Whoops. back. So when n is greater than 30, this is where we're using the central limit theorem. The n is greater than 30 is equivalent to n going to infinity. This is large enough. And the little dot means approximately distributed as, because we're approaching the standard normal random variable. We're never actually equal to it. Okay? So this is where the central limit theorem is coming into play. But this gives us the distribution of the standardized estimators, no matter what we're working with, normal or not normal. Okay. Now there's a point that's really important, and it's that the central limit theorem says that, again, this standardized version of the estimator approaches a standard normal. And what this means is, if you have any random sample of n random variables, and the parameter of interest here is going to be mu, then first of all, we're going to find the MLE estimator for mu, which is x bar. We showed previously that the MLE estimate for mu was equal to x bar. Okay, so that's easy. Then we're going to find the standard deviation. Okay, well, what is that? Well, we know that the estimator is x bar, which is the sum of the xi's divided by n. So now we want the standard deviation of x bar. Well, what is it? Well, we showed that for a sum of independent random variables, the variance of the sum was the sum of the variances. Okay, so the variance distributes across the sum. Each of these are sigma squared, and we end up getting that the standard deviation for x bar is sigma over the square root of n, where this is the standard deviation for x. Okay, so this tells us something about the sampling distribution for x bar. Okay, it says that x bar minus mu divided by this quantity is a standard normal, which tells us that the distribution of x bar is normal with mean mu, standard deviation, sigma divided by the square root of n. Okay, so this is a key point. This is the sampling distribution for x bar. Okay, this is what the distribution of x bar, not x, looks like by the central limit theorem. Okay, all right. So now let's take a look at this a little bit more. Okay, because the sampling distribution of x bar is something that takes a little while to get your mind around. So here's the main idea. It says that no matter what the distribution of x is, x may be normal, it may be Poisson, it may be gamma, exponential, whatever. When we take a large enough sample, x bar has its own distribution, and it's a normal distribution. So when the sample size is sufficiently large enough, the distribution of x bar is normal, no matter what the distribution of x is. Let me kind of show you how this works. So here's an example where we have a random variable that's distributed as an exponential random variable with a parameter lambda equals 3. Okay, this is what the distribution of x looks like. Notice it's nowhere near normal. Okay, an exponential distribution is never bell-shaped, right? Because it starts at 0. Okay, so this is where the mean is 3, but there's no way in the world this is normal. So x does not have a normal distribution. Okay, it has a skewed right tail distribution. However, if we now look at x bar, okay, and we take samples of size 15, notice that the distribution of x bar begins to look normal. And as the sample size gets larger, it looks more normal. And as it gets larger yet, it begins to approach more like a normal. And in fact, if we took n equal to 1,000, the distribution of x bar would begin to very closely approximate a normal distribution, even though x is nowhere near normal. Okay? That's the idea behind the sampling distribution for x bar. It has its own distribution and it's normal for any, and there are some qualifications, but basically for any distribution that we're going to work with, this is true. We don't have to worry. Okay, So here's some homework problems I'm going to have you try, okay? The first is where we have a Poisson random variable, and I want you to generate a program that I want you to write a program that generates 1,000 data sets where each data set has 4 Poisson distributed random variables from this distribution. And you're going to take the average of those 4 random variables for each of the 1,000 data sets. So you should have 1,000 X bar values. And you want to plot the distribution and see if they appear normal. Now you're going to write a program that generates 1,000 data sets of 100 Poisson distributed random variables. So now instead of 4, you're going to have 100. You're going to compute X bar for this 100. You're going to have 1,000 of these X bars, plot the distribution. Okay. You're going to compute the sample standard deviation and compare this to what's predicted by the central limit theorem. Okay? So you're gonna see if the sample standard deviation for this case is pretty close to what's predicted by the central limit theorem. Okay, finally, we're going to look at a case where we have a random variable that's binomially distributed, where n is equal to 50, p is equal to a half. So you can consider this the number of successes in 50 flips of a fair coin. Okay. We're going to suppose that we perform a very large number of trials where we flip a coin 50 times each trial. Okay. And now we're going to count the number of heads that come up on each of the 50 trials and take their average. So xi is going to be the number of heads on the ith trial, okay, where I goes from 1 to 50 here. There should be 1 to 50. Okay. And so you're going to take x, you're going to consider x bar, okay, as the average over those 50 trials. This is not a computer simulation, okay? So the first thing I want to know is, what is the distribution of x bar? Given that you have a sample size of 50 and we know these parameters, what's the distribution of x bar? Okay, notice n is greater than 30, so it's going to be normal, but what's the mean? What's the standard deviation? What's the probability that x bar is more than 27? Okay, for what values of x bar do 50% of the values lie between? And we're going to say the middle 50%. Okay. And if we performed 500 instead of 50 flips in each trial, how would this affect the distribution of x bar? That's a good question to think about. Okay,